In this video we're going to introduce the idea of divergence for vector fields. So the original question was, how can we find the electrostatic field given some random charge distribution? And we come up with this equation here, which was Gauss's law, which doesn't tell us the electrostatic field, but it does tell us the flux of the field. So it's the flux over some surface integral S is equal to the charge upon epsilon naught. Now the problem with this is that this is one equation with an infinite number of unknowns, so all the unknowns are the values of the flux over the entire surface. So maybe we can simplify it by, rather than looking at the flux over the entire surface, if we can think about it in terms of the flux at a single point. So now we have to understand what we mean by the flux at a single point and try and get an intuition of what it means for us physically. So if we think about flux in the way we originally derived it in terms of a mass flow rate, then let's imagine we had some little volume of space, that's it drawn out in a little cube, and it's sitting in some vector field, so it could be sitting in some sort of flow, okay, some sort of liquid. And the arrows that are pointing here represent the arrows of the vector function. So what we're interested in is not the length of these arrows, we're interested in the actual normal component to the surface for these arrows. So for example, this arrow here pointing out, we're not interested in this full length, we're only interested in that part of the length, which is the part of that arrow which is normal to this top surface here. So what we're going to do is we're going to add up all of these arrows that are pointing in and pointing out, and we're going to come up with just a single value, just a scalar, just a number. Now what's that number going to represent? Well, if you were, say, a little element of a little molecule of water in there, if there was more liquid flowing in here, this little volume element, than flowing out of it, then you would feel some force of compression. If there was more flowing out than flowing in, then it would be the opposite. Okay, it would be, if you like, you could call it maybe expansion. Now, we don't use the word compression expansion, we just use a single term for it and we call it the divergence. So if the divergence is a positive value, then what we say is that there's more water or the more liquid or more whatever you want to call it flowing out than flowing in. And if the value of the divergence is negative, it means that there's more liquid flowing in than flowing out, which means that the field would feel like a compression. So that gives us an intuitive understanding of what we mean by the flux at a single point. Okay, so of course in this instance here the flux isn't actually at a single point, it's over a small volume, but we could imagine taking this volume element and doing the limit as the volume element tends towards 0, we would get the single point in the middle. Okay, so that's what we're going to do now, and we're going to look at that idea mathematically and see whether it works for us. So what I've done out here is the same little volume element, and we've got a delta x, delta y and delta z, and it's in a coordinate system here, so the I is a component in the x, j is a component in the y, and k is a component in the z, and that's a little block sitting, say, somewhere here. Okay, that's the base of it. So we're interested in finding the flux through all of the surfaces. So we take the surface at the front here, S1, and the surface at the back there, S2. We know that the normal component of this surface, S1, points in the positive I direction, and the normal component of this surface at the back points out the way, and it's pointing in the negative I direction. Also, if we look at this surface integral S1 of the normal component of the field here, we can see then that if we draw out just a vector function here, so the function's got a component fx in the I, fy in the j and fz in the k, then when we take the dot product of this vector function here with the normal here, well, the normal is just going to be in the positive I direction, so it's the dot product of this with I, so it's going to be I dot j, that disappear, I dot k, sorry, that disappears, I dot j, that disappears, and I dot I, well that's just going to equal 1, so we're just going to be left with the x component of this vector function. So we've drawn that out here, so that's the x component of this vector function. So we're going to make an approximation to this. So the approximation is that we're going to make is we'll find the point fx, okay, that we work out the vector function f of x at, and we'll multiply that by just the area. So that area of that face there, that area of that face there is just going to be our delta y times our delta z. So we're going to do that. So we're going to work out f of x at, well, the x point is just going to be, we're going to come along here a value of x plus the halfway into this box is just going to be delta x upon 2. So it's x plus delta x upon 2, and y and the z components are just equal to the values of y and z. So if we did the same for the back face, the only difference between this line here and this line is that we're now multiplying by minus I, so we're going to end up with the minus f of x. Now if we add both of these two together, we're going to end up with the equation that we see here. Now what we can do is we can multiply the top line and the bottom line by delta x, so we can get a volume element on the top. So we've got this equation here now. Now what we're interested in doing is we're interested in finding the flux at the point. So what we want to do is we make the volume tend towards 0. So we'll take the limit as the delta v tends towards 0 of this thing up here, which is our delta v, and this thing up here. Okay, so I've just put I've not drawn it out right now again, but these lines here represent this. Okay, so the problem with this is when you take that limit, well, delta v just tends towards 0, so we don't get anything. It's not of any use. So what we have to do is we have to scale the whole thing by a factor of 1 upon delta v. So what we can do is if we divide the whole thing by 1 upon delta v, that means that this limit here, well, that's a very small thing divided by a very small thing, always ends up 1. Okay, so the limit of that thing there is always going to end up the value of 1, and then we'll just have the limit here, so it will tend to an absolute limit. Now, we've seen this kind of thing before, whenever we derived the Fourier transform and we looked at extending the period, and when we extended the period off to infinity, the frequency components tended towards 0, so we had to scale that whole thing by a value in the same way that we're scaling this whole thing here by a value. So it's the same sort of thing. If you're interested in seeing that, there's a video. If you click on here and you get in about 12 minutes into that video, you'll see the exact same process that we're doing here, but applied to the derivation of the Fourier transform. So it's a kind of typical kind of mathematical process that you can go through in order to produce results that are useful and valid, so allowing us to produce a limit here. So what we can do then is we're interested in taking that limit there. Okay, so obviously when we divide by delta v here, then the delta x, delta y, delta z, that disappears. So this just pops down to the other end of the equation, which is 1 upon delta v. And when we take that limit there, well, this here, that's nothing other than just the partial f, okay, in the x direction. So it says partial f of x by partial x. If you look at it up there, that's all we've got here. It's just that simple partial derivative. And then what we can do is we can do it for not only those two faces, we can do it for the other 4 faces, and we're going to end up with just the partial fy by partial y and the partial fz by partial z. So if we add all of these up together, this will give us the divergence through the entire surface, okay, or actually the divergence of the surface as it tends towards 0, so we'll get the divergence at a point. So we'll have partial fx by partial x plus partial fy by partial y by partial fz by partial z, and that is called the divergence of the field. And if you like, we can think of that as the mass flow rate per unit volume as the unit volume tends towards 0. And if it's a positive value, it means that there's more flowing out than flowing in. Okay, so we could say that then as a source. I'll write that properly. We could say that point there would be called a source, and if it's negative, then it means that there's more flowing in than out, and we would call that a sink. Okay, so almost done. So what we started off with was one equation and an infinite number of unknowns. Now we've ended up with one equation and three unknowns, so we still can't solve for the electric field quite yet, but the solution will come up in the next couple of videos. But we're well on our way to solving this little problem. I hope you liked this video. If you did, then don't forget to subscribe. Goodbye.